Hi everyone. So today we're going to talk about how you can set initial conditions on a capacitor. A lot of times in problems you'll be just given whatever the initial voltage across a capacitor is. And so today we're going to talk about how you might be able to set that initial voltage. So we're going to start here just from our usual circuit capacitor device equation. So we have I equals C times dV dt. So if we multiply both sides of this by dt, we get I times dt equals C times dV. So if we think about a constant current, if I is not changing with time, then I times dt is some tiny little sliver of time. If I is constant over all times, though, it might seem reasonable to extend this equation that is in terms of these tiny slivers of time on the left-hand side and voltage on the right-hand side. It might feel reasonable to extend those to a full duration of time. So that would give us the I times delta t equals C times delta V. And then, since what we're really looking for is delta V here, the change in voltage across the capacitor, we can rearrange a bit to get the delta t equals I times delta V equals I times delta t over C. So if we take this idea that we had of this constant current, that sounds like an ideal current source. So let's draw that circuit. We have our current source, delivers current I, and for now, we're going to have it just very simply connected to a capacitor, capacitance C. And since the point of this is to look at how we can set that initial voltage drop across the capacitor, let's assume here that the initial voltage across the capacitor is 0. It's starting from scratch. So one thing we can think about is, what if we turn the current source on at time t equals 0? So I'm going to draw a little graph down here. So this is the time axis, and let's put on the vertical axis IC. So let's say that that is the current that is being delivered to the capacitor. So if we turn on this current source at time t equals 0 and it was off before that, that means that there was no current going into the capacitor until time t equals 0. But at t equals 0, it hops up to capital I, current, and then it just stays there for as long as we have that current source on. And let's say it gets turned off right here, and then it'll stay at 0 for the rest of our time. So this rectangle right here, the height is clearly just capital I, constant across this whole box. And the duration of time, let's just call delta t. That's the amount of time that we have left our current source turned on. So if we look, the area of this rectangle is I times delta t. Now we've seen that before. It's right up here, I times delta t. And so if we scale that down by C, that's exactly delta V. So the final voltage that we get across our capacitor, the change in voltage, since we started at 0 equals the final voltage, we're going to get a final voltage across this capacitor of precisely the area of this rectangle divided by C, divided by the capacitance. So that works. That seems straightforward. And one thing to note is that we really only cared about what the area of this rectangle was. We didn't actually care at the end of the day what the actual current I was or what the duration of time was. So that means that we could have just as easily had our rectangle be something like this, where we left it on for longer, but there was less current being delivered, as long as these two areas are the same. We could have also done some really skinny rectangle that delivered a lot more current. Again, as long as the area is staying the same, we get the same resulting voltage across the capacitor. So that all works, but now I want to think about what if we wanted to do this with a voltage source. So now let's draw a new circuit. We're going to have a voltage source this time, and this time we're going to add in a resistor. And if we just tried to connect a voltage source to the capacitor like we did over here with the current source, right, if we look at our capacitor equation, if we turned on the voltage source at some instant in time, then because the voltage source would be in parallel with our capacitor, if we were to set it up that way, that would mean that the voltage source and the capacitor would need to have the same voltage across them. So if we were to just instantaneously turn on that voltage source, it would change the voltage across the capacitor from 0 to V in some vanishingly small amount of time. That would make dV dt enormous. It would make it infinite, and then things would get more difficult. So we're going to avoid that by adding in this resistor here, and that gives us a nice RC circuit that we've seen 100 times. So if we simply use our normal solving techniques for this RC circuit, we're going to get, assuming again as before, that the capacitor starts with 0 voltage across it, we're going to get that Vc of t equals V times 1 minus e to the minus, let's move this out, minus t over Rc. Right, we have our time constant Rc, we have this decaying exponential in here, and so the capacitor voltage starts off at 0 at time t equals 0, and as t approaches infinity, it gets arbitrarily close to settling at this voltage V, whatever voltage we have across our voltage source. But what if we want to do what we did with the current source here, which is we only want to leave this on for some finite, preferably, even a small amount of time. We don't want to need to wait for this very, long, however many time constants until we feel that it's close enough to its settling value of V. What if we want to just do some pulse of voltage, just like we did the pulse of current down here? So the problem with that is that we have this exponential in here, and so that can get things kind of confusing. But one trick is, what if we use the Taylor expansion of an exponential? Right, so we always have that e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., on to infinity with infinitely many terms. So what if here, right, x equals minus t over Rc? So the thing is, that means that this term isn't going to have t at all, it's just the constant 1. This term is going to have t, this term is going to have t squared, t cubed, t to the fourth, etc. So if t is some, reasonable duration of time, like how we had over here, we would have to think about all of these, polynomial terms. But what if we did the really, really tiny pulse of time, like we did in this yellow current block right over here? Then t would be really small. So that would mean that t squared and t cubed and t to the fourth, those would be incredibly small. We can just ignore those because they're going to be so tiny. So now that means that for small t, we're going to have that e to the minus t over Rc is approximately just 1 and then plus x is minus t over Rc, 1 minus t over Rc. So if we use that idea, now we're going to get that Vc of t equals V times, and then we're going to get 1 minus this expression. So 1 minus t over Rc, the ones are going to cancel, and we're just going to get t divided by Rc. So now this is something we can work with. The way we set up this problem right, is that we turned on this voltage source at time t equals 0, and the capacitor started with 0 voltage across it. So that means that Vc of t, since we started with 0 voltage, we could also write that as just delta Vc of t if you wanted to be specific. But let's just think about after our pulse, after we've turned the voltage source off again. So one thing to note, which is key here, is that if we were to simply use this circuit as is and turn on the voltage source, as soon as we turned it off, right, a voltage source turned off just becomes a wire, we would just have this RC, and the capacitor would discharge through the resistor. So the key here is that at the same instant when our pulse of voltage is over, we would simultaneously turn off the voltage source and remove the capacitor from this circuit so that it holds on to that charge, it holds on to the voltage across it. So if we look at what is the change in voltage across the capacitor from beginning to end, from turning on this voltage source to turning it off and grabbing that capacitor away, that is simply going to equal right here, V times delta T divided by RC. Now this looks like what we have up here, where we have the change in voltage across the capacitor equals just some constant. Here it was I over C for whatever I we choose. Here it's V over RC for whatever voltage and resistor we choose, times the change in time. So this is how we could use a voltage source to set an initial condition on a capacitor.